Okay, everything's ready. Hi everyone, welcome to a new scientific moment. My name is Julian. I am a researcher at IOB Labs. For those who are joining for the first time, these are technical talks, and these talks are about what we work on, like blockchain, programming, cryptography, and all of the topics around. We are accepting new speakers, so if you want to present in this talk, and don't hesitate to contact us through the Slack channel that we are sharing the link, or in the research forum. That being said, let me introduce you to Shreemoy Mishra, who is a colleague at IOB Labs. He's a researcher. He works on blockchain state storage pricing, rollups, and payment solution. Before IOB, he taught economics at Delhi Vassar College and Oberlin College. He has an MS in operation research and a PhD in economics from the University of Texas at Austin. He will be speaking about blockchain engineering economics and resource pricing, and he will explain us the economics of system resource used when running blockchain nodes. So welcome, Shreemoy.
Thanks, Ali. Hello, everyone. Hello, everyone. As Ali said, I'm an economist, researcher at IOV, and I'm gonna be. It's meant to be a technical talk, but for a general audience. So we will just go over some of the overview of resource usage when running blockchain nodes. The theme is going to be. There's a bit of a delay here, so bear with me. And the overall theme here is always going to be that we live in a world with finite resources, and blockchains have finite resources too. So one of the examples I was thinking about recently is it's a summer season. A lot of people here on the West Coast traveling to various national parks. And if anyone is going to Yosemite, for example, they have entry by reservations. And the reason, of course, is if you don't have reservations and no limits, then that tends to lead to overcrowding. So lots of parks are kind of putting restrictions around this time on the flow rate of people visiting. And there are similar resource restrictions on blockchains as well. For example, there was a very recent doc by the lead developer of Ethereum's leading client, which is called Geth. The lead developer for Ethereum is this person, Peter Szilagyi, and he gave a recent talk about a week ago. The title of the talk, and I encourage you all to look it up, it's only a 25-minute talk, is he goes over some physics of limitations in processing Ethereum transactions. And since RSK is an EVM compatible chain, we kind of face the same restrictions. And so we'll use some of Peter's talks, the ideas there, to link to the same problems as they show up on RSK. So one of the things that Peter brings up is people new to the blockchain space always complain about the low transactions per second. For example, in Ethereum, they currently process anywhere around 15 to 20 transactions per second, compared to, say, a Visa or MasterCard network, which can process tens of thousands of transactions in a second. And that 15 to 25 figure is for Ethereum. RSK has smaller blocks. And not only are our blocks smaller, but the time between blocks on RSK is about 32 seconds, which is twice of what it's on Ethereum, which is usually about 13 or 14 seconds. So these facts together imply that the transaction processing power in RSK is even slower. So if it's 15 to 25 on Ethereum, we are looking at something like 4 to 5 on RSK. And so people new to the system often wonder, why is it that low? And the answer lies in limitations on what distributed systems can do or what we should allow them to do. And for one, let us recall that not all transactions are the same. Sending ETH from one account to another is very different than a smart contract interaction. So some of the examples that come to mind are a basic transaction, just sending ETH or RBTC. For that, users usually pay something like 21,000 gas. As the transactions get more complex, the gas fees associated with them also go up. For example, sending a token can cost twice as much. Instead of 21,000, token transfer can be around 40 or 50,000. It varies a bit depending on who is sending, who's receiving, but it requires about twice as much work from a blockchain node to process the transaction and verify, and so it costs about twice. But an even more complex transaction would be something that is used in a layer 2 ZK rollup, for example, verifying a snark proof. And that would cost something like almost 500,000 gas in one transaction. Right? So not all transactions are same. When we talk about transactions per second, the nature of transaction matters a lot. And the link here is that the gas we are charging users, what they're paying for, is really a reflection of the underlying costs of operating a blockchain system. Lots of nodes connected to each other in a peer-to-peer fashion. Loosely speaking, these rates, these ratios reflect the idea that a snark proof verification requires much more effort to execute and verify than we need to just go through a simple send. Now, some of you may not be familiar with this idea of thinking about resource usage and gas. But a simple way to think about it is just think of block limits, which are often in terms of gas. Ethereum nowadays has a maximum possible block limit of 30 million gas. On RSK, it's 6.8 million. Now, no matter how the block sizes are, we still want to execute these transactions in about 1 second or less. So one way to think about the relationship between gas paid for a transaction and resource use is just divide the time. We want to execute every block inside of a second. 1 second is about 1 billion nanoseconds, and divide that by the block size. And then we can obtain a cap for how much time resource a transaction can take per gas. And so for Ethereum, we come up with something like 33 nanoseconds per gas consumed. For RSK, since our block size is smaller, we have higher tolerances. Transactions can take a little bit longer per gas, and will still be okay. But that's what it's kind of linked to. Resource use is compute resource, network resource, and what's going to be most of this talk is going to be on storage resource, not so much on network or computation. We'll see that in a bit, that main resource problems in the blockchain space are showing up on storage and not in other arenas. Because most smart contracts are actually not that simple to, not that complex to compute. Real complex part of transactions like generating a snark proof happens off-chain, not on-chain. From an economics perspective, there's this conflict between the private benefit that transaction centers get and the costs they impose on the network. Right? So if someone generates NFT, mints an NFT, or interacts with a Uniswap-like protocol for a DeFi trade, then they derive some personal private benefit for it. But that transaction then has to be processed and verified by thousands of other nodes. And that's a cost on all the other nodes, people running full nodes. Let's recall some of these steps that every node must take. Every node must store, verify, and relay the transactions received to its peers. I want to break this up into 3 overall sources of costs. One is computation, the other is the network bandwidth, and the final is going to be storage. Of these three, we'll figure out that only the miners are being paid for these costs. If you are someone who's running RSK node or a Bitcoin node, you don't get any of these fees. So you're primarily running a Bitcoin node for your own reasons, such as altruism. You just want to help the network, or you know that this most secure way of running your own wallet and maintaining your balances is to run your own full node. Okay. There's no explicit compensation. Those compensations only go to miners or in proof of stake systems, people who have pooled in some ETH to generate blocks as part of the pool. And that's why we call them these social costs. Users derive private benefits, but everyone running a node has to somehow pay for these costs. And the computation costs are kind of the lowest at this point. You don't really need fancy hardware in terms of a CPU. Most blockchains, RSK, and even Bitcoin, especially, can be run even on a Raspberry Pi. You don't need a very powerful CPU, unless you want to run something like Solana. Solana is one of the rare blockchain networks that has very specific hardware requirements, like you need 32 threads or a lot of RAM. But for most blockchains, RSK, Bitcoin, Ethereum, you don't need a very powerful CPU. The second source of costs is the network bandwidth. And this can be significant for people running blockchain nodes like me from our homes. Okay. I have a reasonably good connection, but I don't really want to use all of my upload bandwidth. It can be a significant amount. So these costs are significant, but we can manage them. We can manage them by putting limits on how much data we upload to our peers. And the other way I control my costs is I don't run my Bitcoin node or RSK node all the time. You can just limit how long the node is online in a given day or a week. And so computation and network are manageable costs for people who want to run their own nodes. What's really proving challenging in the blockchain space for all networks is really storage. And so we should move on a little bit to considering what the types of storage are in blockchain systems, because it's sort of two layers of storage. The first storage that people outside of the space also know are what I just called storing blocks. Blocks contain transactions, and so it's what we can just think of as historical state. Just storing history of all prior transactions so you can verify them. The second type of storage is the real resource constraint, and that is what we call blockchain state. State in Ethereum, for example, or RSK, is data like account balances, what's an account's nonce, smart contract code, smart contract storage cells. So that sort of application data is what we call state. The one simple way to think about it is our own regular bank accounts. The entire history of our account, every deposit, every withdrawal, every interest you've earned, or every fee you've paid, that's just history. You don't need all that history to run a payment app. For running a payment application, you just need the current state, which for us is just how much is the balance. So there's this distinction between history, which is every possible transaction in the past, and the current state, which is what we are after. And to run applications, whether it's on your mobile phone or a blockchain app, history doesn't really matter. What matters is state. And going further into storage types, we see that to validate transactions, we need state. So we're going to slow down a little bit here so people can differentiate these ideas. Now, of course, state can be reconstructed from history. And this is the reason why when someone starts up a blockchain node the first time, it takes so long to sync. We have to download the history first and then replay the entire history to arrive at the current state. Okay. So that's the distinction between state, which is a snapshot, and history, which is a collection of everything that has happened in the past, starting from the Genesis block. Now, every transaction reads from state and modifies a part of state. Even a simple send transaction, if you send someone one RBTC, that would involve reading your account state, figuring out you have enough balance, and then adjusting those balances for the sender and receiver. So every transaction modifies state somehow. So what we are after is this impact of state changes on a node's performance, because the state is evolving with every transaction, and the limitations on transaction processing, transaction verification, everything depends on how fast can we do these things, reading from state and writing to state. So we'll just think about that for a second and check if there are any. I'll usually be taking questions at the end, but I think Huli is watching the chat there, and he'll let me know if there are any questions that need to stop for. So just a quick check. Huli, is there any reason to stop right away? Huli?
No questions so far.
Okay, cool. Yeah, so just to kind of recap, the state is evolving with every single transaction, and every node on the network, whether there are hundreds of them or thousands, they must sort of replay these actions in the same consistent manner. Everyone must read from state, write to state, delete the part of state if necessary, and they must all do so in a consistent manner. Otherwise, we'll break consensus. So this state modification is kind of linked in a way to the way we also think of cryptocurrencies. Now, real currencies like fiat, it's very common to see things like what is money? It's a medium of exchange, a unit of account, or a store of value. And what blockchains bring to this space is one more interpretation, and that interpretation is that money is just a different kind of memory. Now, I did not come up with that term. Money is memory is actually from a 20-year-old paper by Narayana Kocherlakota. And in this paper, what the author shows us in a technical model really is define memory as a record of all past interactions. Okay, so everything that has happened. And this may be true even in on-chain systems and games where players interacting with each other. And what Kocherlakota shows us, anything that we can do in an environment with money, we can replicate all those interactions and states with just memory. But the opposite is not true. Everything that you can do with memory cannot be replicated with just money. Memory is just way more richer. And so in a sense, money is just a primitive abstraction of memory. It just sort of summarizes the vast richness of interactions that people have in economic spaces. And this matters for decentralized systems like Bitcoin and RSK, because essentially what Satoshi showed was Bitcoin operating as peer-to-peer money, but that was all entirely made possible by peer-to-peer memory. People running nodes, storing all these transactions, modifying the state, which in Bitcoin is just unspent transaction outputs. They don't really have balances. Okay? And so what we are doing with these decentralized systems is making peer-to-peer money, or even programmable money. It's not made possible through peer-to-peer memory and peer-to-peer memory manipulation, which is also just a different name for decentralized computing. So again, stop for a bit to recall why this matters. Is just every application, whether it's an NFT or a DeFi contract, all of that is about every blockchain node modifying memory in the same way. And storage, state storage especially, is where this stuff happens. And so now we'll kind of go towards these limitations of what Peter calls physical limitations, just pure physics. So let's say you want to run a Geth node. Geth is the leading implementation for Ethereum. It's based on Go. And let's say I want to run that reference implementation on my own machine, and my machine has about 8 GB of RAM and a hard disk. It's SSD, not the fastest, but it's SSD about 512. So naturally, that SSD is not big enough to store all of historical data. Bitcoin history is about 550 GB. Ethereum is much more. Right? But that's not a big problem because external drives are not that expensive anymore. You can get an external drive with 2 terabytes SSD for about $100, a little bit more. So that problem is not a big one. Historical data, we can store that. Okay. But what about state, which is the other type of blockchain state memory that we're talking about? In Ethereum, the current size of the state is somewhere around, depending on how you measure it, anywhere from 40 to 60 GB. And let's recall that to process transactions, what I need to verify them is state, not history. And so if the state, it's relatively smaller, 40 to 60 and not a terabyte, but that's what I need to process and verify transactions. But my PC only has 8 GB of RAM. And so that state is not going to fit on RAM. And I'm doing other stuff with my machine, not just running a Bitcoin node or a blockchain node. And so most of state, this 40 to 60 GB on this machine, will be on disk, most likely on the external drive. And so to verify transactions, it's a lot of reading and writing to disk. So the limitations on transactions processed per second really boil down to the rate at which we can read and write to these disks. And so let's go through this exercise a little bit to come up with some numbers of what's possible in terms of transactions per second. And to do that, you need to recall a little bit about how the EVM stores state, account balances, and contract code, stored cells. All of this stuff in Ethereum and also in RSK is stored in a data structure called a trie. Some people pronounce DRIE as tree because it comes from retrieve, but it's also fairly common in the community to pronounce it as trie, and I'm going to use that. So it's a tree data structure in which each node can have up to 16 child nodes. That's in Ethereum. In RSK, it's different. But the interesting bit is Ethereum gets lead developer, Peter calls it the bane of Ethereum. Okay, let's take a quick look at why he calls it the bane of Ethereum. But again, before we move there, I want to remind everyone, RSK's trie is a bit different. We use a binary trie, not a hexary trie. Binary tries are a bit deeper. Hexary tries are shallower and kind of wider. There are other differences, like RSK uses a unitrie. So the same trie contains account balances and all contract code and storage cells. Everything is a single trie. Ethereum has multiple tries, but the abstraction is really, I think we'll just look at a cartoon version of a trie first. And so this is what I'm having a little bit of a lag issue here with the slides on screen and on my machine. So let's see. Okay, cool. So blockchain state is stored in this tree structure. We have the root node, and then the root node in Ethereum can have up to 16 child nodes, but that's not enough. 16, we want to store all the account balances at the end. And so we need to go one more level deep. So if we have 16 child nodes per each node, then at 2 layers deep, we can have 16 squared, that's 256. Right? So we keep adding layers until we get the desired number of layer nodes at the very end, at the very bottom, that can fit all the accounts in state. Now for Ethereum, there are about under 200 million accounts. I think Peter says the number is closer to 175 million, so less than 200 million. Now, if you have a tree structure and you want 175 million accounts at the very bottom layer, then how many layers do we need? And that's just, you take the log of 175 million, log base 16, and we arrive at a number of around 7. So for a simple send, the idea is, if it's a simple send transaction, the simplest possible transactions, what are we going to need in terms of disk I/O? That's where we are going with this. So if we need to read the sender's account and the receiver's account from a trie that has 175 million nodes at the lowest layer, then we take the log and we figure out that 175 million log base 16 is about 7 or 8. So on average, 6.5 internal nodes. And then finally, we find the node that contains the balance for the sender. And we find the node that contains the account information for the receiver. So for each of them, we need to look up about 7.5 nodes. So both of them together, about 15 nodes. So that's the data we need to read and update, 15 nodes in a trie. Going forward, these trie structures are really in the computer's RAM. They're not how they're stored eventually on disk. Ultimately, on disk, they are stored through a key value data store, like LevelDB is the one that used in Get and also in RSK. And so when you go from these 15 nodes to storing the information in binary on the disk, each node requires about 15, LevelDB adds about 7 more layers of computations. So we multiply each of these nodes, read and write, becomes a 15 times operation on disk. And the 15 nodes for sender and receiver become a total of 105 I/O ops. Now I should remind you of a potential future SciMo talk. Our chief scientist, Sergio Lerner, is working on some experiments with with LevelDB. And so there are some optimizations that we may be making in RSK in the future. But for now, just recall that for a simple send transaction, we want to read the sender's node and the receiver's node. That's a total of 15 nodes, counting internal nodes to get down the path in the tree. And in terms of disk I/O, there are further overheads. There are further overheads for things like computing the root hash of every node, working your way all the way to the top of the tree to get the new state root hash, and then propagate blocks. Once the miners have done these I/Os themselves, everyone running a full node has to run these disk I/Os too. So just to update the sender's balance and the receiver's balance, we are looking at 105 times 4, about 420 disk input-output operations. And that's for simple send, not a fancy smart contract call. That will be much more complex. But this is going to give us the limits. So if we need 420 I/O ops for a single simple send transaction, how many such transactions can I process and verify on my machine? If all of this information stays on disk, then this is what I'm looking at. If the external drive that I'm storing the blockchain information on is a simple HDD, then the number of transactions we can process is not even 1. It's like 0.2. If you have a reasonably fast SSD, then we can get to 200 transactions per second. And if you use the most advanced SSDs, professional grade, then maybe 2,000 transactions per second. Still less than Visa or MasterCard. And remember what Ethereum is. They are at 20 per second. So 2,000 is possible, but they're choosing not to go there. And RSK is at 4 to 5 transactions per second. We can go faster, but we're choosing not to go. Why? Because of these limitations, they're only going to get worse in the future. So the key thing here is we need state to verify transactions. And since state doesn't fit on RAM, we have to go to disk I/O, which slows things down. And so the key idea is, how do we avoid disk I/Os? Right? The easiest bit is buy a computer with a bigger RAM. Right? Try to keep all of this, or as much of it as you can, on RAM, so you won't have to go to disk. Now, this is a reason that Ethereum developers usually work on computers with uh, pretty large RAM amount, 64 gigs. This is also a reason why Solana requires nodes to have 200 or more in terms of RAM. Okay. But if you want to run Ethereum yourself on your machine today and you don't have 64 gigs, you're kind of out of luck. Most people who run nodes either have very advanced hardware at home or they just rent some cloud space. It's easier to run it on AWS or Azure than to do this at home. Furthermore, the state is growing much faster than RAM is. And so Peter kind of says this is a brick wall and that Ethereum is, and all blockchains, including RSK, not right now, but in the future, are on this potential death trajectory. Because RAM is not growing as fast as the state is. And if that keeps happening, we'll never hit a higher level of transaction processing and verification ability. If we increase block size today and encourage the state to grow faster, well, that only pushes this death trajectory, this brick wall, further. It'll happen sooner, not later. And also, this makes it less likely that end users, normal, ordinary users, will ever run their own nodes. Right now, it's possible to run a Bitcoin node or RSK node at home, but that's because the state isn't that big as Ethereum's. So if you don't take care of state growth now, it's going to be really bad for decentralization and can lead to overdependence on centralized players like Infura. So you just have to give up on this idea of independent peers and everyone just signs up for an API account on Infura. Okay, we don't want that future. We want the system to be as peer-to-peer and distributed as possible. So what are some ways to avoid this future? The first approaches are kind of purely engineering approaches, smarter ways of caching the data, smarter caches, new schemes of prioritizing which bits of state to keep in memory. For example, a transaction that users who are using the blockchain more frequently, we can keep their data on memory, or we can charge them something to keep their data in RAM and not go to disk, or do some kind of pruning, in-state pruning. So there are lots of intermediate states, and some of those intermediate states can be finalized, and only the finalized state makes it to disk. The other intermediate states we can just get rid of. So those are some engineering applications. I want to wrap up this talk here with some applications, some approaches that we call engineering economics that kind of combines engineering approaches with some price incentives, because we think those are much more impactful than just trying to patch the system with a new cache or so the top three, I'm going to go over the top three solutions that we have in mind. The first one is really simple. The first one says, let's reprice some of the EVM opcodes. Now, those of you who are smart contract developers will know these as opcodes like sload to read memory from a storage cell, or sstore to read and rewrite the value in a storage cell, or balance to check the balance of the contract account or an end user's account. We can make these I/O operations more expensive. So again, who are developers here will know that an sload costs 200 gas on RSK right now. So we could make that closer to what it is on Ethereum, which is around 2100 gas. So that's one way to reduce I/O operations, is to disincentivize them through higher prices. The second approach is something called storage rent. And the novelty here is that in blockchain storage, it's kind of the current paradigm is users store data in state, they pay once, and they store it forever. Right? There's no concept of paying for how long you store information. Storage rent changes that, and it introduces a time component or a duration component to say users, developers, whoever's interacting with the state should kind of pay some fees for how long data is stored in state. Because the current system is really weird economics, pay once, store forever. So that's the second approach. So one is EVM repricing. The second is storage rent, charge rent for how long data is stored. And the third approach which is also getting a lot of traction, is what's called off-chain solutions. So try to offload a lot of transactions to something like a ZK rollup or an opportunistic rollup based system in which most transactions move off-chain to a different blockchain, and then only some state change information is pushed to layer 1. And at IOV Labs, we are working on all three of these approaches, on repricing, on storage rent, and offloading transactions. The one that I've been involved with a lot is the middle one with storage rent. And this is what Peter also calls the real solution, because the others do not really target state size growth. There are other incentives on the number of disk IO, for example, the first one, but doesn't directly influence state size itself. Storage rent targets state size itself because it encourages people to reduce how much they are storing, how long they are storing. And as I mentioned, we're working on all of these approaches for RSK at IOV Labs. Because limited resources within real world or in the blockchain space, we have to manage them well. Or if we don't manage them well, we can really muck up the systems. Okay. I'm going to wrap up with an image here that will be familiar to many of you. It is interesting at first and then horrifying later. And so some of you may have seen this image of this traffic jam on Everest, and people jumping, clambering on each other to get to the top and take a picture for a selfie. Okay. And the same things can happen in traffic jams and blockchain networks in which the resources get really, really constrained. So that is what I wanted to kind of go over today. The constraints are real, and we have to watch out and plan ahead in the future. And we have to manage them not just with smart engineering, but we also need to manage them with smart economics. And we always need to keep our eyes on the future and not get greedy about growing state too fast now, because that will only bring greater challenges in the future. So I think it's a good place to stop. Thank you very much. And to encourage questions, I'm just going to leave you and discussions for later. I'm going to leave you with these three high-level approaches that we are using and developing at IOV to handle state size growth. So thank you very much. Juli, you can.
Thank you very much, Shreemoy. Let's move to the questions and answers. So far, there are no questions. So at first, thank you very much, Shreemoy. It was a really interesting talk. We have a comment from Sergio saying that it was an amazing talk. You can see the comments in the screen, in the comment section. So
I've not been following that. But yeah, those who are listening in, I would really encourage them to take a look at Peter's talk from last week. He gave it at ETH Prague, and he touches upon a lot of issues. They are much more dire for Ethereum than RSK. RSK is relatively younger, so we feel safer, but we will face the same difficulties sooner or later. So yeah, thank you very much for the chance. See you all next time.
Thanks, Shreemoy, and yeah, see you soon.
Okay, guys, thank you. Congratulations, Shreemoy. Excellent
It's
presentation.
still live.
Okay. Thanks for your time, guys.
Of course, thank you.
See you soon.